You ever wonder how a camera can just capture a massive landscape in one tiny picture? Or how a simple flashlight can turn your hand into a giant monster on the wall? Well, the secret sauce isn't some super complex physics. It's actually a really elegant idea from geometry called similarity. So today we're going to dig into the geometry of optics and see how this one core concept literally shapes the world we see. So here's our plan. First, we're going to build our foundation in the optics of geometry. Then you're going to get to test your skills in the practice gauntlet. And finally, we'll walk through all the logic in the producer's hints.
All right, let's dive right into part one. We're going to lay down all the essential rules and ideas here. Think of this as us getting the master blueprint before we start building anything.
Check this out. Long before we had digital cameras, people used this thing called a camera obscura. It was basically just a dark box with a tiny hole in it. And the magic wasn't in some fancy lens. It was pure geometry. See, light travels in straight lines. So the light from the outside world created a perfect set of similar triangles, a big one outside the box and a tiny flipped one inside. That's how you project a huge scene onto a small wall. And that idea, similar triangles, is what we're all about today. Okay, let's get our key terms straight real quick. Similarity is just a fancy way of saying one shape is a scaled up or scaled down version of another. That scaling number, we call it the scale factor, or just K. Now here's a real game changer, AA similarity. It means if you can prove that just two angles in one triangle match two angles in another, then bam, the triangles are automatically similar. You're going to use this one a lot. And finally, for polygons, that formula there, it's a foolproof way to find the sum of all its inside angles. Now, this is absolutely crucial. When you scale a shape, the sides and the perimeter scale by that factor K. But the area, here's the kicker, the area scales by K squared. Think about it. If you take a 4x6 photo and you double the sides to make an 8x12, you're not using twice the ink. You're using 4 times the ink. That's K squared in action. This is a huge deal everywhere, from architects scaling up blueprints to visual effects artists rendering textures. The classic shadow problem. You see these all the time for a reason. They're a perfect real-world example of similar triangles. The trick is knowing that the sun is so incredibly far away, its light rays are hitting everything nearby at the exact same angle. That means the triangle formed by a lamppost and its shadow is similar to the triangle formed by you and your shadow. So all you have to do is follow these steps. Set up a simple height-to-shadow ratio, and the answer will pop right out. Want to know a super fast trick for finding the sides of a regular polygon? Forget wrestling with that complicated interior angle formula. Just do this instead. Find the exterior angle. It's just 180 minus the interior one. Then divide 360 by that number. Seriously, that's it. It tells you exactly how many sides it has, so much faster. Okay, pay attention because this is a classic gotcha question. You're going to see problems with a small triangle tucked inside a bigger one, with a line parallel to the base. It looks confusing, right? Like you're missing information. But the secret is they literally share an angle at the top. That shared angle, plus the matching angles from the parallel lines, gives you guessed it, AA similarity. So the little triangle is just a mini-me of the big one. All right, you've got the blueprint, you've got the tools. Now it's time to step into the practice gauntlet and put it all together. Okay, it's your turn to get your hands dirty. For each question I put up, I really want you to hit pause and give it a shot yourself. Sketch it out, work through the steps. Don't sweat it if you get stuck. The important part is really trying to solve it. You ready? First up, a quick warm-up. We've got two similar triangles, ABC and DEF. If side AB is 5, and its matching side DE is 15, and side BC is 8, what's the length of its matching side, EF? Hit pause and see what you get. Okay, workout number 1. You know this one. The classic shadow problem. There's a 5-foot pole, and it's casting a 2-foot shadow. Right next to it, a big tree casts a 10-foot shadow. The question is, how tall is that tree? You know the drill, hit pause. And for our next workout, we've got one of those nested triangles. There's a line DE that's parallel to the main base BC. We're told that the segment AD is 2, DB is 4, and the big base BC is 9. So what's the length of that smaller base DE? Go ahead and give it a shot. Okay. Deep breath. It is time for the boss fight. We have a trapezoid here. The diagonals are drawn in and they cross right at point E. This creates a bunch of smaller triangles. Your mission, should you choose to accept it, is to find the ratio of the area of that little top triangle to the area of the big bottom one. This one's tough, so really take your time with it. All right, pencils down.
Let's see how you did. Now, we're not just going to give you the answers. That's not the point. We're going to walk through the logic, the how and the why, so you can nail these problems every single time. So for that warm-up, the very first thing you always want to do is find that scale factor, Te. We just compare the two sides we know that match up, DE and AB. So you take 15 divided by 5, and boom, our scale factor is 3. The new triangle is 3 times bigger. So we just apply that multiplier to the other side. 8 times 3 gives you 24. And that's your answer.
The shadow problem is all about setting up the right proportion. You've got height over shadow for the pole, which is 5 over 2. And we know that ratio has to be equal to the height over shadow for the tree. So let's call the tree's height h. That means 5 over 2 equals h over 10. You do a little cross multiplication, and you find that h, the height of the tree, is 25 feet. Okay, that nested triangle one was tricky, and here's the trap. The key thing, and this is where people trip up, is that you need to compare the side of the small triangle to the entire corresponding side of the big triangle. So it's not AD over DB. It's the small side AD, which is 2, over the whole side AB, which is 2 plus 4, so that's 6. Now our proportion makes sense. 2 over 6 equals the small base DE over the big base 9. Do the math, and DE comes out to exactly 3. And now for the boss fight. The whole secret here is spotting the hidden similar triangles. Because the top and bottom of the trapezoid are parallel, you can find those Z angles, the alternate interior angles. That proves the top triangle is similar to the bottom one using AA similarity. So the scale factor is just the ratio of their bases, 4 to 10, which simplifies to 2 to 5. But, and this is a huge but, the question asks for the area ratio. So what do? We have to square the scale factor. So you take 2 squared over 5 squared, and you get the final ratio, 4 to 25. So, pretty cool, right? We've seen how this one powerful idea, similarity, connects everything from an ancient camera to a shadow on the ground. We know that when you scale a 2D shape's sides by k, its area scales by k squared. So that leaves me with one final question for you. What do you think happens when we jump into 3D? If you scale up a box or a ball by a factor of k, how does its volume change? It's a really fascinating extension of this whole idea. Thanks for diving in with me on this one.